In this exercise, we want to obtain the three-dimensional model of a tricycle to get a simulation, a three-dimensional simulation. So we have a tricycle which is represented by the figure here. I have some parameters, geometrical parameters, and some state variables that move with time. Of course, we will have the degrees of freedom and the speed of the center of the front wheel here. Also, I will have a state variable, the angles of each wheel, which are named S1, S2, S3. So for the first wheel, second wheel, and third wheel. So the third wheel is a front wheel. First, I will have to get the state equation of this model, and then to be able to draw it with a three-dimensional picture that will be done with Python. And then I will provide, thanks to the state equation, I will provide a three-dimensional model of the tricycle. So my model is represented here. And if I look from the top, I will have here X and Y. Here I will have the body and here the two rear wheels, the steering wheels here and here, but it's not, I have only one wheel, so the one wheel is represented here like this. Okay. Here I have X and Y, the center of the rear axle. Here, so it corresponds to a part of the degrees of freedom, but I have also this one. Delta has the degrees of freedom, and of course the heading, which is named theta here. So all this one will be a state variable. I will have also to add the dynamic speed variable, which corresponds to the speed of the center of the front wheel. So it's named V. It's a scalar because the direction is the direction of the front wheel. And as state variables, I will have to add S1, S2, S3, but it cannot be seen from the top. So I will apply the composition of the speed from the top view, and I will represent in the frame of the car. So I will represent like this the frame of the car. Okay, so this one corresponds to the X direction and the Y direction in the frame of the car. So if I apply this, I will consider this point, the center of the first rule. And we know that the speed is like this and is directly related to S.1, where S.1 is a variation of angle of the first wheel. The first wheel is this one. Second wheel, third wheel. So the speed vector I consider is like this, is directly related to the variation of angle. So this is why the speed vector here is R S.1 0 0, because I have only a component with respect to X, no with respect to Y, and no with respect to Z, which is like this. Okay, so now if I consider this point, and as a second point I consider this one, I get the vector which is represented green here, and this vector represented green has the following coordinate L, E, and 0, where L is here the distance between the rear axle and the center of the front wheel, and E is represented here is the distance between the center of the rear axis and the wheel number 1. So if I apply the Varignon formula, I will have here the speed of this point. So it is V cos delta V sine delta 0 plus the cross product between this vector, so L E 0 vector, and this one will be 0 0 theta dot. So if you prefer, this corresponds to omega. Here this point corresponds to A, which is this point. This one corresponds to this point M, which is here. And here it is the speed of A. Okay, and here it is the speed of M. It is plus. So this corresponds to the Varignon formula. So from this, if I only consider the first component, I obtain that R S dot 1 is equal to V cos delta plus E theta dot. Okay. Now, since theta dot is equal to V sine delta divided by L, I will obtain that S dot 1 is equal V cos delta plus E V sine delta divided by R. Okay, now I can do the same, not with this point, but also with this point. Now this vector will change and I will have here L minus E, because it will become like this. This is why I obtain S dot 2 equal, so it will be excuse me, here I have also R, so here we have V divided by R multiplied by cos delta, so here minus E due to the minus I have here, so minus E sine delta divided by L. So it was for the second wheel, and now for the third wheel things are simpler, since they are directly related to the speed vector of the front wheel. So I will have here V divided by R. Okay, so why I wanted to get this one? Because to have state variable, I should consider the state vector, so let it call x, and the state vector of my system are the degrees of freedom, but I have also to add the velocity of the front wheel. So I will have here x, y, theta, okay, the velocity, delta, and here S1, S2, S3. So now, to get state variable, I should have variable like this, x dot equal y dot equal theta dot equal v dot equal delta dot equal s1 dot s2 dot and s3 dot. Okay, and here I am only allowed to put state variables, so x, y, theta, v, delta, s1, s2, s3, but also the two inputs u1 and u2. And nothing else should be written except the parameters, and the parameters we have here are e, which is assumed to be known, so distance here, e, l, which is known, so here it's 2 meters, here it's 3 meters, it's this distance, and also the radius of the wheel, which is known to be 1 or 0.5 meters, something like this in the exercise. Okay, so now I will have, if I use the model of the car, so I have already computed S.1, S.2, S.3, so probably I will have to write them here. V divided by R cos delta plus E divided by R V sine delta. Here V divided by R cos delta minus EV sine delta divided by L. Whoop, excuse me, here I need also a L. And here V divided by L. Now for here I will use the model of the car already studied in another exercise, but here I can understand that I have the speed of m of this point of A here. It is v cos delta multiplied by cos theta, and here also the speed of A multiplied by sin theta. Here I will have v sine sine delta divided by L, and here u1 and u2. So all what I have here correspond to the state equation of my tricycle. To draw my tricycle, I will have to consider first the two sketches. The first sketch corresponds to the body, so here, and this body has different points, here, here, and so on, and all these points are in the matrix B0, which corresponds to the sketch of the body of my car. And also I need to have a sketch of one wheel. So from these two sketches I will be able to copy them, to move them, to rotate them, translate, and so on, in order to draw the car. So for this, I have put everything in homogeneous coordinate. This is why I have ones here on the last line, and here it corresponds to all points here and here. The same for the wheel. For the wheel, I have ones everywhere here to have homogeneous coordinates, and I start from 0. So here I start from 0, then I move here following one radius, I move here, and so on. I come back and I do something like this. Okay, so all points, the pair of 2 points correspond to one of the segments here. So I have to build these two matrices and then to draw them. So this is what I will do now with Python. I have here my program. I take here the sketch for B, and the sketch for the wheel is made with a for loop here. Okay, so from the two first line, so the four first columns by a simple rotation. So all these rotation are in the Autolib library. I will be able to, from applying the rotation in a for loop, to build the sketch for the wheel. It is what I obtain here. I will run it. I can see here one wheel, red, and the car, so the body of the car, of the tricycle, represented here blue. Now I will have to to put at the right position. To move the sketch, B0 and W0, I will need some transformation matrices. So the translation in homogeneous coordinates is a 4-4 matrix where I have 1 1 1, so identity here for okay, and here v x v y v z, a 1 here and 0 here. This corresponds to the translation. Okay, now I will also to rotate my object, and the rotation matrix are given by rotation of a vector w is also a 4-4 matrix, where here I have an exponential matrix of 0 0 0 minus omega x omega y minus omega z, here omega x minus omega y and omega z. So it is a skew symmetric matrix. Here 3 3, 0 for the translation part, the 1 here for the homogeneous coordinate aspect, and here 0 0 0. So if I multiply a sketch with ones on the last bottom line, if I multiply by such a matrix, I will always obtain a sketch with 1 at the end. So this rotation is a rotation around a vector omega like this, and the angle corresponds to the norm of omega. So take care, here it's an exponential matrix, not component by component. Okay. Now, how can I, from this shape, so this sketch, which is given normally here, let's say here, like this, then I have to move at the right position. So you can understand that I will have to translate like this, I will have to rotate and so on. So we can understand that the one which is here, B, at the right position, can be obtained from the initial sketch B0 as follows. First, B equal B0, so B0 is this big matrix. I will rotate it, so I will multiply by rotate of W, so I will rotate with respect to 0 0 theta. So I turn like this. I have only a component with respect to the third dimension, and I will have to multiply here to translate, so to multiply by a translation matrix, and this translation corresponds to this x and y. So here I will have x and y, but also I have to go up in order to take into account the fact that the wheel that the body is not on the bottom, but there is some height that is due to the fact that is supported by 3 wheels. So here I have to add r, where r is this distance. This is for the body. Now I will have for the wheels. So I have 3 wheels, 1, 2, 2 and 3. So let's consider the first wheel, which is given here. First, I start with a wheel which is something like this. In this direction, the wheel is like this. So the axle like this, okay, with respect to x like this. So if I turn the wheel, I will rotate around x. Of course, to give a position to put this here, I will have to perform different transformation. First, I need to rotate of p divided by 2 to have the same orientation as the initial body. So r, which is given here for this one, r, excuse me, maybe w1, w as wheel, is a product of many matrices. So here I have from w0, first I rotate by 0, 0, p divided by 2 to give the same orientation as the initial body. Then once the wheel is, let's say, like this, so x is now like this because of the rotation, and y is like this, I will have to turn around itself like this to give the right angles, and the right angle is given by S1, and the rotation is with respect to y. This is why here I have to rotate 0 S1 due to the fact that it is, I turn around y. Okay, so now I will have to translate to put with respect to the initial body sketch. I will have to translate left with respect to y, and the translation is minus e, because e, it is on the negative side, and e is the distance between the center and the wheel. So here I will translate with respect to 0, minus e, and 0. So now my wheel is correctly oriented with respect to my initial body. This is why now I will have to apply the same transformation as the body itself. So the translation with respect to x, y and r, as here, multiplied by the rotation with respect to 0, 0 and theta. Okay, now I will do the same for W2. So W2 is exactly the same, except here, where I have here a E, because I do not have to move right, but left. So on the positive direction with respect to y. The y, everywhere, it is exactly the same. Now for the first wheel, which is given here, it will be different. Okay, so the third wheel, the front wheel. We can understand first that we start from W0. We multiply the rotation by 0, 0, p divided by 2 as previously. Of course, I rotate also to give the right angle I also rotate to give the steering direction, which was not the case for the other wheels that had no steering. This is why here I have to rotate with respect to 0, 0, delta. Then I will have to translate of 0, 0, L to rotate as previously with respect to 0, 0 theta, and translate with respect to x, y, and r. Okay, so if I do this, I have the following Python program. Where in this program I have made the function draw tricycle. I extract, so I initial my state like this. So here I have x, y, theta, and v delta, s1, s2, s3. And here I draw the tricycle. I call this function. I have the sketch of my body as previously, and the transformation for the body is called here RB. So it's a composition of the translation here and the rotation here. Okay, so it will be applied to the body sketch and also to each wheels at the last moment. Oh, I recognize here the rotation by divided by 2, and the rotation with respect to the corresponding angle, here the steering angle, and then I draw them. I switch to Python. I run this program, and I can see here my car, which is represented at the right state. For the last question, 3, I have to provide a simulation with my three-dimensional graphic representation. This is why I need to implement in a for loop an integration of the state equation. Recall that the state equation are given here. This was those I have obtained with my state variable here, x, y, theta, v the speed, delta the steering angle, here s1, s2, s3, here the acceleration, here the steering, and this corresponds to the evolution function f of x and u, which is implemented here. So first I extract from the state all the variable I need. Then I return the corresponding array of dimension 8. Okay, here it means that I have an acceleration, but also I move the steering wheel. This is my parameters. This is the initialization for the state variables, my for loops, and at each step I draw the tricycle. So I run my Python program, which is here. I run it, and I can see my car moving, turning like this. So the acceleration is small, but I can see that the wheels are rotating, and we can understand that the speed is adapted to the fact that the car is turning on itself. The front wheel has the speed given by v. So v is still positive, but now due to the steering angle, the car goes backward.